So, the presence of glides and screw axis in other crystal systems can occur. We have the trigonal axis, we have the tetragonal axis, and then the hexagonal axis. So, these three axes correspondingly can have the screw translations symmetry. So, the screw translations can be 1/3, 2/3 with respect to 3-fold axis, 1/4, 2/4 and 3/4 with respect to the 4-fold axis, and so on. So, that means that trigonal, tetragonal and hexagonal systems will also have the presence of glide planes and screw axis. That is shown here, the screw axis are shown here, and the corresponding symmetry information which we have discussed before as well are appearing here. Now, as I said in the last part a few minutes ago, we have to see what happens with a cubic system. I already gave a hint that it could be along the 3-fold direction. So, we could have the cubic symmetry, but then I was discussing about the hierarchy of operations. The hierarchy of operations come in such a way that we talk about the nature of the lattice first, and then we talk about the presence of the screw axis and the glide planes. This will have a very important repercussion when we see the X-ray diffraction patterns, because the X-ray diffraction patterns we analyze with respect to the various values we see from the presence of these reflections, and the presence or absence of these reflections are governed by the way in which this space group develops. And therefore, some of these elements, the presence of the C centering, the presence of the I centering, will introduce what are known as systematic absences. And so also the presence of the 2-1 screw axis and the mirror and the glide planes. But the screw axis and the glide planes will affect only the so called projection reflections, whereas the general reflections are affected by the centering operation. And that is why the priority is given to the lattice type, and then the 2-fold and the translation involved symmetries like 2-1 and n and so on. Right. We go to the next slide where we shift the system now to orthorhombic. Orthorhombic is more or less an extension of monoclinic discussion we had so far to 3 dimensions. This is very straightforward, because in case of the monoclinic system we have a single 2-fold axis, whereas in case of the orthorhombic symmetry we have 3 2-fold axes intersecting at a point, and these 3 2-fold axes come at 90 degrees with respect to each other. So, because of the fact that whenever there is a 2-fold axis, 2 of the angles should be 90 degrees. If there is another 2-fold axis perpendicular to the given 2-fold axis, the other 2 angles will be 90 degrees, the consequence of which is all 3 angles should be 90 degrees, and that is what happens here. Alpha, beta, gamma are equal to 90 degrees. So, A not equal to B not equal to C, alpha, beta, gamma are 90 degrees defines the so called orthorhombic system. The way in which these 3 2-fold axes are disposed with respect to each other is illustrated here. As you can see, this is the intersection point. So, you have along the x direction, you have along the y direction, you also have it along the z direction. The minimum symmetry therefore is 2, 2, 2, and that is the point group symmetry 2, 2, 2, which is described here. So, you have a 2-fold axis associated with a direction coming towards us, and as a consequence we have a 2-fold axis in plane, and there are 2 2-fold axes intersecting with each other in plane, and therefore this would be the illustration of that. So, you also have this circle a little darker than necessary to show that the 2-fold, 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 there are 3 2-fold intersections. So, suppose there is an object here, it sees the 2-fold up here and goes over to that, and after having gone to that position it sees the presence of the 2-fold, but then this 2-fold is on the back side of it, which is at an angle of 90 degrees with respect to that, and as a result it goes over to this position, and this now sees the 2-fold here and comes back to this position and vice versa. So, it keeps therefore 4 equivalent points, and those 4 equivalent points, now you are experts, you can write them down yourself. The 4 equivalent points were 2, 2, 2. You can also write the equivalent points for the next set of symmetry elements, because we have been discussing this issue many times already. So, maybe I should just write once to remind you of what we are talking about. So, here this now represents a primitive axis. Here it represents an improper, sorry, not primitive, proper rotation axis, improper correction, it is not primitive, proper rotation axis, improper rotation axis, and then the last one which is improper. The combination of 3 MMM will represent the 3. Now, how does MMM come about? MMM comes not about 3 improper rotations, because we already showed by Euler's theorem that 3 improper rotations will not go in conjugation. So, MMM therefore is not MMM, but it is actually 2 by m So, it is a combination of a proper and an improper rotation. That is the point group which we have discussed before. So, instead of writing 2 by m consistently, we can just make it simplified to MMM. So, please note that MMM did not come from 3 improper rotations combining with each other, then you would be violating the Euler's theorem. So, therefore, it is 2 by m. So, whenever you see more than 3 mirror combinations coming, like for example, later you will see in the tetragonal system 4 by MMM. It actually means it is 4 by m, 2 by m, 2 by m. So, if you remember that carefully, in fact, it is a part and parcel of your understanding this whole course, then you will never make a mistake. Okay. So, 3 proper rotations 2, 2, 2 now will take us to the point group symmetry 2, 2, 2. And now we have to see how many lattices which we have to consider to combine 2, 2, 2 with. In the case of the orthorhombic system, we have all possibilities. We have the primitive one, we have the body centered one, where we have at the center of the body a half position. So, please count the number of lattice points for every one of these systems. In case of the primitive system, it is 1. In case of the body center, it is 2. What happens in case of the F centered? In case of the F centered, we have 1, 2, 3, 4, and then 2 half ones 5 and 2 half ones 6. So, totally how many are there? 1 corresponding to the edges and 2 more corresponding to the centering with respect center of these axes and 1 at the center. So, totally it will be 4. So, the number of lattice points for a F centered orthorhombic lattice will be 4. And of course, we can have A or B or C separately centered like in the monoclinic system, and then we will have therefore the C centering. So, C centering means also it could be A centered, it could be B centered, because it just depends upon how you define the values of A, B and C. You see, in the case of an orthorhombic system, you can always interchange A, B and C. So, when you interchange A, B and C, the correspondingly the A centering, B centering, C centering will change. So, they are one and the same. So, therefore, we have 4 types of lattices with which we have to combine the 3 point groups. So, 4 lattices, 3 point groups with no translational symmetry associated with them. And therefore, you have generating a system like P 2, 2, 2, P MM2, P MMM. So, these are the 3 crystal systems which you can generate with P. With I again you can generate these 3, with F again you can generate these 3, and with C centering also you can generate these 3, and you can keep on doing that. So, you see the number of space groups will increase considerably now. We had something like 17 space groups or so until now it is adding up considerable number. So, orthorhombic in fact is one of those systems which has the highest number of possible space groups, because it has the combinations of primitive I centered lattices, F centered lattices, as well as A or B or C centered lattice. So, the possibility of a molecule to crystallize in orthorhombic symmetry must be the maximum, and so the possibility of the occurrence of orthorhombic symmetry in overall crystal systems, if one analyzes the database, orthorhombic systems are many more compared to the rest of the crystal systems. It does not mean that orthorhombic is the preferred crystal system, It so happens that it allows for several possible space groups. This is a point which you should remember. So, point group symmetry as well as the lattice symmetry combinations therefore give us the space group, that you are very clear now. Now, we also have possibilities of two-fold screw axis. The two-fold screw axis now is with respect to A, with respect to B, with respect to C, and therefore, we can have glide planes with respect to all of A, B, C. We can also have combinations of screw axis and glides. So, you see now that the three proper axes can take, for example, screw axis. So, that means we can have a space group like P 2 1 2 2, P 2 1 2 1 2. We can also have a space group like P 2 1 2 1 2 1. In fact, all three are possible, and it depends upon how the molecule decides to pack itself inside the unit cell. So, we can therefore invoke the insertion of the two-fold screw axis by getting space groups P 2 2 1 2 2, P 2 1 2 1 2 and P 2 1 2 1 2 1. P 2 1 2 1 2 1 is the most favorite space group for organic molecules, particularly if they carry an asymmetric carbon, and that is because it allows for maximum flexibility in the system. When we study the space groups in detail, we will derive those equivalent points. What are the equivalent points that can come for P 2 1 2 1 2 1, and see what I mean by that. You remember this class, and then we will discuss P 2 1 2 1 2 1. When we discuss the space group, I will make clear why there is so much adjustment space available for rather flexible functional moieties organic molecules. Glide planes. Glide planes, again, we can have with the primitive lattice, we have three two-fold axes perpendicular to each other. So, we can have all three glides A, B and C. So, we can have combinations of the two-fold axis with the glides like P2AB and things like that. We can also have all glide combinations like PNAB or PBCA and so on. So, you see the number of possible space groups we can generate in a case of an orthorhombic system increases enormously. And so, this is I am talking only with respect to the primitive lattice. We can go to the I-centered lattice, we can go to the F-centered lattice, we can go to the C-centered lattice. For example, we can have a space group like C2AB. So, all these space groups now become possible, and now you see the flexibility that is available in the solid state. Until now, we were talking about the restrictions available in the solid state. We were talking about the fact that translational periodicity locks the molecules into their respective positions. But now, the way in which the space groups can manifest themselves as we go further into the higher symmetry space groups, starting from triclinic, monoclinic and now in orthorhombic, we see there is a considerable amount of flexibility. So, the molecules are very happy now, because the molecules now can crystallize into their choice space groups. In fact, the molecules can have more than one choice space group, and that is where the issue of polymorphism comes. And this is an issue which is a big issue for pharma industries. We will discuss that towards the last few classes. Now, the combination of the screw and glide also is very crucial. Which screw can combine with which glide plane? Of course, we have to keep our Euler theorem in mind, because we cannot have different kinds of combinations which will give rise to the IIP, for example, is a possibility, but anything beyond that is not a possibility. And therefore, we have to have something like PMM2, PMCA, for example, and things like that, which will now correspond to the MMM point group symmetry. PMCA is MMM point group symmetry, which means it corresponds to 2 by M, 2 by M, 2 by M. And when we say PMCA, it will be 2 by M, 2 by C and 2 by A. Okay, so, the glide planes will always invoke the presence of 2 2 2. So, that is why the minimum symmetry you should have in an orthorhombic system is 2 2 2. Unless you have three two-fold axes intersecting with each other, in general you will not be able to generate orthorhombic systems. And so, those are the restrictions, all right, but the flexibility is immense. So, using the immense number of flexibilities, the solid systems in solid state can arrange themselves. But there is always systematics which is associated with these arrangements, and that is where we have an advantage to identify and locate the positions of the atoms in any given crystal system and in any given space group. Now comes the next set of crystal systems. We go to the tetragonal system. In the tetragonal system, of course, there are several possibilities. One of them is illustrated here, the so-called four-fold symmetry. That is also illustrated here. Remember that in a tetragonal system we have A equals B not equal to C, alpha, beta, gamma are 90 degrees with respect to each other. The moment we have these three angles at 90 degrees to each other, we invoke automatically two intersecting two-fold axes in addition to the presence of the four-fold axis. The presence of the four-fold axis generated will make the axis unique with respect, and we fix that as the C direction. So, we fix the C direction to be the unique axis direction, and that is why it is written here Z. So, we take this to be along the four-fold axis, and then the innumerable number of two-fold axes can be present here. But the simplest space group which point group we can consider is the four-fold. Just the four-fold, which takes the objects into four different positions as is illustrated here, along with the four-fold notation which we have in here. So, this generates four equivalent points. Having generated four equivalent points, we can also generate four equivalent points if we take the combination of the four-fold symmetry with the presence of 4 1, 4 2, 4 3. So, if you take for example 4 1, from this point to that point we will have a 1/4 translation added. From this to this we will have a 2/4 translation added. From this to this point we will have a 3/4 translation added. On the other hand, if we have P4 3, from this point to that point we will have a 3/4 addition added. This to this it will be 2/4 addition added, and then in this to this will be 1/4. So, the handedness associated with this will change. In one case it is going this way, the screw axis, in the other case it goes the other way. So, these two screw axis operations P4 1 and P4 3 are opposite of each other. If you consider P4 2, it is equivalent of if equivalent of a 2 1 screw axis effectively. So, it is just a single operation. It is dichotomy in that particular case, whereas in case of 4 1 and 4 3 they go in opposite directions, the screw operation. If you look at the possible Bravais lattices associated with the tetragonal system, one can show P and I only exist, which probably we will do in the form of an assignment later. But if you consider the two lattices that are allowed, only P and I are allowed. Any other lattice like F for example, or A, B, C centered, because of the fact that we have A equals B as an additional condition which makes the basal plane square, the moment there is a square we cannot have it centered effectively, and therefore the centering of the faces is out. See, whenever you have a square base, you go back to your previous classes where we discussed these 5 plane symmetries. In that we had a square symmetry, that is the little p, the primitive lattice in the four-fold symmetry. There we cannot have a center, because if you have a center you can generate another four-fold there, and so it is degenerate. So, whenever you have A is equal to B, you cannot have that face centered. So, because this face cannot be centered, that face cannot be centered. Likewise, these are at 90 degrees with respect to each other. So, the 90 degree angles can also be face centered. Unless you have these 4 centered, we cannot have the other 2 faces centered, and therefore F is ruled out. This is the logic which I am trying to give you. One can work it out mathematically, but I thought that logic is good enough for our current discussion. So, we have the primitive lattice and the body centered lattice, where you will have a additional lattice point at half. So, the Z equals 1 here, Z equals the lattice number of lattice points is 1 here, number of lattice points is 2 there. Because of the fact that A is equal to B, we will also not allow one single face to be centered. So, A, B and C separately being centered is also ruled out, and therefore, we have only 2 possible lattices in the tetragonal system. So, the job now is to combine these lattices with the possible point groups. The first point group is with 4, so all the possible combinations are shown here. The number of equivalent points initially is, in these cases of primitive lattice, is 4, whereas in case of the body centered lattice it will be double that. So, we will have z equals 8. So, as you all know that we add a half along x, half along y, half along z. So, having seen the possible space groups here and the I centering is adding this, we see an example of I4 is given here. Now, the type of rotation axis which we just now discussed can be described here 4 1, 4 2, 4 3. You see that exactly what I talked about 4 1 if you start 4 3 if you start from this point, that point will be 3/4 added and this point will be 1/4 added. So, the rotate, if you now look at the 4 3 rotation, it is this way, the left handed rotation, and in this particular case it is the other way around. This is the anti-clockwise and this is the clockwise rotation. So, 4 1 is anti-clockwise, 4 3 is clockwise rotation, and that is also illustrated by this combination here. 4 2 automatically generates only the half point. So, there is no distinction between one direction and the other. This will be more interesting to discuss when we go to the trigonal system, but the trigonal system is an issue which we will see later. If time permits, we will go into it, because we have to cover a lot of other things in this course. So, we may not specially discuss them, except that I would like when we go to the trigonal system I will mention it, of course. So, let us see what other possible point groups that can occur with the tetragonal system. That is the next slide. Next slide will take us to 4 by m. So, here it is written tetrad, that essentially means a 4-fold rotation. This is from a textbook where they use tetrad and dyad for 2-fold, and so this has been taken from the textbook, but we will say this is the 4-fold. The 4-fold can be proper and or inversion, that means proper or improper axis along the z direction, and that we specify it first. So, the 4-fold rotation is along the z direction all the time, and the mirror is now going to be perpendicular to that operation. So, if you see here, the mirror is indicated perpendicular to the 4-fold. So, the presence of the 2-fold axis is immaterial, it is 4 to 2. So, in this particular case the system can be just 4 by m. The other 2-fold axis will be automatically implied when we derive the so called equivalent points. For example, here I4 is shown to have x y z, x bar y z, y bar x z and y x bar z. That will be the 4-fold operation, and along with the 4-fold operation, if we add half plus half plus half plus to each of x, y and z, we will generate 4 more points. So, there will be 8 equivalent points for I4. The possible space groups with 4 by m combination, however, are phi 4 by m, p 4 2 by m, phi 4 by m, phi 4 2 by n, I 4 by m, I 4 by 1 by a, and there are additional ones which you can add depending upon the nature of the rotation axis. Remember, we can have both 4 1, 4 2 and 4 3. So, what you see here is only the 4 2 ones given, 4 1 and 4 3 are also possibilities. Now, when 4 1 and 4 2 are considered possibilities, there is probably not a possibility of an n glide. So, we have to work out why only these are given, and that is something which could probably be taken as a homework by you guys, so that you can have a look at it and then see how it all depends upon. So, there is a 2-fold axis, proper or improper, along the x direction. See, when we describe the tetragonal system, since A is equal to B, the 2 directions are degenerate. So, that means A can be B, B can be A, and because of this degeneracy issue, we represent only one of the axes to be associated, let us say, with the A direction. So, once we associate that with the A direction, the second 2-fold axis will be in a direction which is perpendicular to 1 1 0, which is along 1 1 0. See, the directions in crystal systems are normally given by 1 1 0. In fact, we are going to discuss that in the coming classes or in an assignment later on. So, 1 1 0, if we show it in square brackets, it represents a crystallographic direction. So, 1 1 0 is a direction which is along 1 unit along A and 1 unit along B. So, 1 1 0 therefore is the direction about which the 2-fold axis gets represented in this case. So, we can have 4 by m and the possible space groups are written here, and this is an illustration which shows how the mirror plane can be perpendicular to the fourfold axis. Having seen this, I think we can go to the further discussion on the P4. Space groups, possible space groups are listed here. You see many numbers will develop because of the presence of the fourfold axis, proper and or inversion, because we can have 4, we can have 4 var, we can have 4 1, 4 3 and so on, 4 2, 4 3. Now the presence of the 4 bar system is interesting because we already saw in the previous case 4 by m. We also saw 4, but we have not seen the 4 bar operation. So the 4 bar operation will also introduce, will have the possibility of proper, and this is an inversion axis on the fourfold symmetry. So that means in the z direction we can have not just the fourfold rotation alone, we can also have the inversion associated with the fourfold rotation. So that generates the equivalent points accordingly. I do not think there is enough time for us or space for us to discuss that in this particular course, how to get the equivalent points and so on. So what we will therefore do is, we will just illustrate as a particular space group like 4 2 2, let us say. Now this space group 4 2 2 has additional twofold symmetries. See, just compare this diagram with the diagram we have here. This has only one fourfold symmetry, and that is an allowed point group symmetry in a tetragonal system. That means there is no symmetry which is imposed in the direction perpendicular to the z axis. So that means the x and y, even though there is the twofold axis is implied in them, it is not specifically mentioned, because in this particular case when the mention is made of 4 2 2, you see the number of equivalent points will increase. From 4 it will go to 8, because there are additional twofold symmetries which occur due to the fourfold operation. So this fourfold operation will take 4 of these twofold screws, and between these 2 screws we develop additional twofold screw operations. So the number of available symmetry operations will start increasing. In fact, they will multiply. So as a consequence, you will end up with several possible space groups written like this, and therefore tetragonal has also a very large number of space groups that can be generated. Tetragonal still continues to have different kinds of symmetry combinations, because we have not discussed the proper, improper axis associated with it. So this is the one which I mentioned earlier, 4 by m, 2 by m, 2 by m. It can also be written as 4 by m, 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 and that is the maximum symmetry we can have in a tetragonal system. So the tetragonal system therefore has a combination of point groups which are 1, 2 here, 3, 4, 5 and 6. So there are 6 possible tetragonal combinations: 4, 4 by m, 4 2 bar 2m, 4 2 2, 4 mm and 4 by m, 2 by m, 2 by m. So all these point groups combinations can be now combined with the possible Bravais lattices, which are 2, primitive and eye-centered. So therefore we get a plethora of possible space groups which we can generate in a tetragonal system. Now we go to the issue of a trigonal system. We will discuss a little bit on the trigonal system at this point. The trigonal system is just like we have a z-axis representation of the fourfold, we have now a z-axis representation of the threefold. So the threefold now is associated with the z-axis. I purposely wrote this ulta arrow to show that we can either have it in this direction or in that direction, it is immaterial. So it so happens that people generally write that, and people think it is only along that direction we should have the threefold. So I thought I will write it opposite to show that the threefold rotation axis can also be in the opposite direction. So we can therefore have only these point group combinations. We can have threefold, which is just generating these 3, and then 3m, which generates 6 of these, because it is 3 followed by a mirror. Notice here it is not a 3 bar m, it is 3 followed by a mirror operation. So first we operate the threefold and then mirror invert it. and 3 bar m operation, which is again an operation which takes the threefold object onto an inverted 3-4 object. So, you see that there is a symmetry between the 3 open circles and a symmetry between the 3 closed circles. So, consequently the threefold operations generate different kinds of equivalent points compared to the so far discussed in terms of tetragonal and orthorhombic. But what is the most important point is to consider the direction of rotation axis. So, the direction of rotation axis when we refer to the point group symmetry and eventually in the space group is taken to be the z axis. So, the z axis representation of the presence of the threefold is a consequence of the presence of the lattice. So, when we say that threefold is along the z axis, we are already implying that there is a lattice corresponding to that. And how many lattices are possible in the trigonal symmetry? We will take it up in our next discussion. So, at this point we can sort of conclude that the threefold, the fourfold are along the z direction in case of the tetragonal and the trigonal symmetry, and the tetragonal symmetry has p and i, and with the I we will get an additional set of points added with half plus along x, half plus along y, half plus along z to every relationship which we generate in terms of equivalent points associated with the primitive lattice. So, the other thing is we have seen in the case of the orthorhombic system is that there are 3 two-fold axes perpendicular to each other. So, whatever property we associated with one axis in the monoclinic system can be associated with the other two, and also the possible existences of 4 types of lattices will generate a large number of space groups. So, now if we can add up all these space groups, we are going very quickly towards the 230 possible space groups. We are not going to count them now, but eventually we will reach a stage where we will finish up all the 230 space groups.